In this videotape, we're going to continue with our work on applied maximum and minimum problems. This is the second tape on the max-min problems. You should first watch the part 1 tape. Both tapes have a list of problems that accompany them, so you don't have to copy the problems off of the blackboard, but rather get the sheet listing all the problems from the MATLAB supervisor, and that'll help you in working out the videotape. This is meant to be the second tape in the series on max-min problems, so the problems are going to be a little bit more complicated. The first tape, basically a lot of rectangle problems with variations. Here it's going to be a miscellaneous problems. Each one is sort of different, and let's see what we can do. The first problem, an open box is to be made from a square piece of cardboard, 12 inches on each side, but cutting out equal squares from the corners and folding up the sides. How long should the edge of the cutout square be in order to obtain a box of maximum volume? What is the maximum volume? So we're starting with a square piece of cardboard, 12 inches on a side, and we're going to be cutting out squares from the 4 corners. They should be equal squares. And what I've just cut out, these are being cut out and are going to drop to the floor, and then we're going to fold on the dotted lines to produce the box. We start with a piece of cardboard 12 inches on a side. And what I plan to do is to take from this piece of cardboard, I take out corners, squares from the 4 corners, and fold up along the dotted lines. And you can Scotch tape this and to form this box. And we're interested in maximizing the volume of this box. Now the squares have to be of equal side. If you take out a large square here and a small square here, you can see you would not be able to fold up and make a nice box like that. Okay, so we're starting off with a piece of cardboard 12 inches on each side. We're cutting out equal squares from the 4 corners. This will all drop out like we have here, and then we're going to fold on the dotted lines to produce this box. Okay, now we want to maximize the volume of the box, and the volume of a rectangular solid is, of course, length times width times height. Okay. Now, we originally started with a piece of cardboard that was 12 inches on a side. Let x represent the length of the edge of the cutout square. So this is x, this is x, this is x by x, this is x by x, this is x by x. Let's think about this. We're forming a box. We're interested in getting the volume of the box, which is going to be the length times the width times the height. Now, originally this was 12 inches long. When I take out an x here and an x here, this dimension here would be 12 minus 2x. Because originally it was 12 inches long. I took out an x here and an x here. So what's going to be the length of the box is 12 minus x, or 12 minus 2x. Similarly, because it's a square, this is also 12. Take out the x and the x. This is also 12 minus 2x for the width. So we have the length and the width. Now, watch this. See, we cut out the square x by x. When we fold, that x that we cut out, that becomes the height of the box. Okay, so we'd like to get whatever we want to maximize in terms of only 1 letter. Here we have it in terms of 3 letters, but we see that the length is 12 minus 2x, the width is 12 minus 2x, and the height is x. Think of it again, 12 inches on a side. Take out the x and the x. The length is 12 minus 2x. the width also 12 minus 2x, and the x that you cut out folds up, becomes the height of the box. So now we have our typical problem. Want to maximize a function that's maximize something that's a function v that's a function of only one letter. Now there is an interval on x. X, well, can x be anything? It can't be negative. It can be either an open or a closed interval, depending on how you do it. You learned about that in the first videotape. But certainly, we would all agree that x can't be negative, and x can't be more than 6 inches. Because if I were to actually take 6 inches, if this is originally 12 inches on a side, if my square is 6 inches by 6 inches, the 4 squares that I cut out drop to the floor and there's nothing left. The whole piece of cardboard has been spent on the 4 corners. So obviously 6 would be the absolute maximum. You couldn't do 7. 6 you could do, but it would be a very funny box because you'd be holding nothing. I would take my piece of cardboard, I'd cut out squares 6 inches on the side, everything would fall on the floor, I wouldn't have a box. Or I have a box of volume 0. On the other side, on the other hand, let's say I decide that what I take out is 0 on a side. So therefore, here's my box. The length is 12, the width is 12, but the height is 0. So those are the two extremes. If you decide that a closed interval makes sense, some people might prefer to use an open interval and say, look, I want to actually do this. Obviously, I'm not going to go to 6 because there's no box, and I'm not going to use 0 because, once again, there's no box, in which case it's an open interval. We can, as you learned in the first videotape, we can finish the problem off either way. Okay, let's see what we have here. Let's take it over here. V 12 minus 2x times 12 minus 2x times x, multiplying these two binomials together by FOIL, first, outer, inner, and last. First is 12 times 12, 144. The outer terms, 12 times the minus 2x is minus 24x. The inner terms, again, minus 24x, so that's minus 48x. And the last terms, minus 2x times minus 2x is plus 4x squared. And now distributing the x through the parentheses and rearranging the terms, 4x cubed minus 48x squared plus 144x. Now we want to maximize v. And we're going to take the derivative, v prime, derivative of v with respect to x, and set it equal to 0, and look for the critical numbers. We don't have to worry about, critical numbers are basically points in the domain of the function where the derivative is 0 or doesn't exist. This is a polynomial which is always going to exist, so we just have to worry about the stationary points, the places where the derivative is 0. The derivative here is with respect to x, 12x squared minus 96x plus 144. We could set this equal to 0. We could factor out a 12, x squared minus 8x plus 12. And we can divide both sides by 12. And 0 divided by 12, of course, is 0. And then to factor, we need two numbers that multiply to plus 12 and add to minus 8, minus 6 and minus 2, giving us two answers, x equals 6 and x equals 2 for a critical numbers here. Now, there are two ways to finish up the problem. Method 1 would say that we're working on the closed interval where x is between 0 and 6, in which case we're maximizing a continuous function on a closed interval. and it's guaranteed to have an absolute max and an absolute min. And the interval runs from 0 to 6. And we make ourselves a little chart, and any critical numbers that fall in between, for example, 2 gets included. And we figure out the volume in each of these instances. The volume formula, we can work from the first one, will be the easiest. If x is 0, of course, the volume is 0. If x is 6, 0 times 0 times 6, the volume is 0. That corresponds to not cutting anything out, in which case it's just a flat sheet of cardboard, or cutting everything out and there's nothing left. And the most interesting case, of course, is when x equals 2, the dimensions become 12 minus 4, 8 times 8 times 2. Or 64 times 2, or 128 cubic inches. Now, traditional way of handling this, the largest of these is the absolute max, the smallest the absolute min. Of course, the absolute minimum volume is 0, occurring at these extremes. This is the absolute maximum. So the absolute maximum volume that you could get would be a box of 128 cubic inches, and that would correspond to cutting out an edge of 2 inches. So the answer would be, in this case, x would be 2 inches. We're going to say how long should the edge of the cutout square be. In order to maximize the volume, we should be cutting out squares 2 inches on a side from the 4 corners, producing a box which would be 8 by 8 by 2, or 128 cubic inches. Now, if you feel that this should really be an open interval, then the way you would proceed is there is only one turning point on this open interval. X equals 2 is the only critical number on this interval. Let's see what kind of a critical number we have. If we go x against v prime, if we substitute in the value of 2, take a value less than 2, a value more than 2, and see what happens to v prime. If you substitute in 1, 12 plus 144 minus 96, it's certainly going to be positive. If you substitute in 4, and you can, in fact, use the factored form 12 times x minus 6 times x minus 2 to see with positive times negative times positive, the product would be negative. The first derivative is positive, so the function is increasing prior to 2, decreasing afterwards. If it's increasing and then decreasing, this must be location of a local maximum. So there's a local maximum at x equals 2, but there's only one critical number, so only one turning point. Only one turning point. We have this continuous function with only one turning point on this interval. Then if it's a local max, it must also be the absolute max. So the absolute max occurs when x equals 2 inches. So either way, you get the same answer. In our second problem, we have the following. If 400 people will attend a film when the admission price is $1.50, and if the attendance decreases by 40 for each 50 cents added to the price, what price of admission will yield the greatest gross receipts? Now we want to maximize the gross receipts. We can call that G, which is basically the number of people attending the film multiplied by the price per person. That they're willing to pay to go to the movies. Now we're interested in, of course, representing g in terms of only one variable, and then we can proceed as we usually do. What I'm going to do is let x equal the number of 50-cent price increases. This would be an easy way. This will make the problem a little bit easier to solve. In other words, right now we have 400 people attending at $1.50 per person. Now, the attendance is going to decrease with every price increase. The price, of course, will go up. If x is the number of price increases, okay, and the attendance decreases by 40 for each price increase, then 400 minus 40x represents the number of people attending. For example, when x is 0, before you start to increase the price, 400 people come. After the first price increase, when x is 1, you're down to 360, and so on. Now, x represents the number of price increases, so the price will be $1.50 plus 50 cents times each price increase. Let's see if this makes sense. X is 0, we had, this is 0, this is 0, we have 400 times $1.50, which is correct. If x is 1, one price increase, the number of people attending would be 400 minus 40, or 360, and they're going to be paying $1.50 plus 50 cents times 1, so $1.50 and 50, so $2 a person for the 360 people. If you have 2 price increases, then you've decreased the total audience by 80, but the price is now up $1. Okay, now there's a very clear interval on this problem, and it is a closed interval. X could be 0, which means we leave things the way they are now, 400 people at $1.50 a person. What is the maximum that x can be? Well, price-wise, obviously you're unrestricted, but after 10 price increases, nobody's coming anymore, so you've gone too far. Okay, clearly starts off that you're going to make more money. Whereas when x is 0, that's one extreme. When x is 10, it's the other extreme. And we're looking for that ideal price in the middle where you may have fewer people, but the price has gone so high that it still gives you the greatest gross receipts. Now, if we want to multiply this out, we want to maximize g. Perhaps you can either do it with the decimals, or if you wanted to change it to fractions, 1.5, so that would be 3/2 plus 1/2 x. If you prefer, you could either do the decimals or do it with fractions. Either way, multiplying by FOIL, 400 times $1.50, or 400 times 3/2 would be 600. That's first. The outer, 1/2 x times 400 would be 200x. The inner, minus 40x times 3/2 is minus 60x. 2 goes into 40 20 times 360, so minus 60x. And the last, minus 40x times 1/2 x, minus 20x squared. So we want to maximize g, which is 600, plus 200 minus 160, so plus 140x minus 20x squared. And we're going to take our derivative of g with respect to x, or g prime, which is 140 minus 40x, set it equal to 0. 140 equals 40x, dividing both sides by 40. X is 14 over 4, or dividing by 2, 7/2, or 3.5. 3.5 price increases. Let's think what that means. Then at this 3.5 price increases, what will the gross receipts be? It'll be 400 minus 40 times 7 halves, and then three halves plus 1/2 times 7 halves. How many people will attend? 2 into 40, 20 times 7, 140, 400 minus 140, 260 people will attend, and they will, let's see, we have 7 quarters and 3 halves. 3 halves, 1.50, 7 quarters, 1 3/4, so they're paying $3.25 a person. Or think of it this way, we increase the price 3.5 times. 3 price increases of 50 cents, and then a half of a price increase. So 3 times 50, $1.50, and another quarter, $1.75, increased from what it was, which was $1.50. So $3.25 is the price. 260 people we expect to attend. In this particular case, the gross receipts would be 260 people times $3.25 a person. It works out to be $845. Now the question is this the actual maximum? Well, we can make ourselves a little chart. The interval, remember, was from 0 to 10. The only critical number that we got was 7 halves, or 3.5. When x was 0, going back to the original equation, when x was 0, that meant 400 people at $1.50 a person. That was $600. At 3.5 price increases, it's $845. And at 10 price increases, going back over here, the price would be $650, except 0 people will be attending. 400 minus 400, 0 people paying $650 a ticket, and therefore the gross receipts would be 0. The absolute min would be $0. The absolute max, which is what we're looking for, would occur with 3.5 price increases, and the gross receipts would be $845 at that time. Okay, so we have the maximum gross receipts at $845, 260 people attending at $3.25 a ticket. Remember, this 3.5, this is not a price, this is a number of times we increased the price by 50 cents. The original price was $1.50. 3 50-cent price increases, another $1.50, that's $3, and then another half of an increase to make it $3.25. Okay, in the third problem we have the following. A wire 36 inches long is cut into 2 pieces. One piece is bent into the shape of a circle, and the other piece is bent into the shape of a square. How should the wire be cut so that the total area enclosed, in other words by the circle and the square, is a minimum? How should it be cut to maximize the area? I'm going to take my wire, which is 36 inches long, and put a cut in at some point, let's say X inches from one end. So it's now split into 2 pieces. One is X inches long and one is 36 minus X inches long. And I'm going to take the X inches and I'm going to turn that into a circle. And the 36 minus X inches I'm going to form into a square. So I have X inches for the circle and 36 minus X inches for the square. And I want the area of the circle plus the area of the square to, in one case, be a minimum, in the other case, to be a maximum. Okay, the sum of the total of the areas. Now, we consider a circle of radius r. We know the area of the circle is pi r squared, and the circumference of the circle, which is like the perimeter of the circle, is 2 pi r. Similarly, if the square is, say, s inches on a side, the area of the square would be s squared, and the perimeter of the square, the distance around, of course, would be 4s. Now, the perimeter of the circle, the distance around the circle, I'm taking this x inches of wire and bending it into a circle. So the perimeter of the circle is x. And the perimeter of the square is going to be the 36 minus x. The perimeter of the circle is x inches. I take the x inches and I bend it into a circle. That x becomes the perimeter or the circumference of the circle. The 36 minus x gets bent into a square. The perimeter of the square is 36 minus x. Now, I want to consider the total area, which is the area of the circle plus the area of the square. The area of the circle, of course, is pi r squared. The area of the square is s squared. In one case, we want to maximize, and the other case, we want to minimize the total area enclosed. Now, as in all the other problems, we need to get it in terms of only one letter. We have it in terms of r and s. But here we have the means to get everything in terms of x, because since x is equal to 2 pi r, this leads us to the fact that r is x over 2 pi. X is equal to 2 pi r. X was the circumference of the circle. It was 2 pi r. So r must be x over 2 pi. On the other hand, since the perimeter of the square was 36 minus x, this leads us to the fact that s is 36 minus x over 4. S is 36 minus x over 4. So we do have r in terms of x and s in terms of x, so that we'll be able to get a in terms of only one letter, namely x. A is pi r squared plus s squared, but r, as we said, is x over 2 pi. So x over 2 pi squared times pi, and s is 36 minus x over 4. Pi r squared plus s squared, replacing the values that we found for r and for s. Okay, so we have a in terms of only one letter, and we need an interval on that letter x, and the interval is the closed interval from 0 to 36. If x is 0, then no wire is used. I mean, we cut, right? We don't cut at all. No wire is used for the circle. The entire 36 inches is used for the square. The other extreme, x is 36 inches, no wire is used for the square, and everything is used for the circle. Or you can cut it someplace in between and use part for the circle and part for the square. And we're looking to see what will maximize the area, what will minimize the area of the sum of the areas of these two figures. So let's see what we have. A is pi times x over 2 pi squared. Let's make this x squared over 2 pi squared. X squared. Now what is 2 pi squared? It would be 4 pi squared. 2 pi quantity squared is 4 pi squared. Pi times, like a over b squared is a squared over b squared. The x is squared, and the 2 pi squared 2 pi times 2 pi, giving us 4 pi squared. Plus, once again, if this is like a over b squared, it's the top squared over the bottom squared. 36 minus x quantity squared over 4 squared, which is 16. Now let me rewrite this. I'm trying to set it up so that finding the derivative will be fairly simple. These are constants, this is a constant. So let's write this. Pi over 4 pi squared is 1 over 4 pi times x squared plus 1 over 16 times 36 minus x in parentheses squared. Pi over 4 pi squared gives me 1 over 4 pi times x squared plus 1 over 16 times 36 minus x squared. Now, if I want to get dA dx, or a prime, we have the sum of two products. Okay, using the product rule. These are actually like mini products because the first in each case is a constant. So, the first times the derivative of the second, but the second times the derivative of the first would just be 0 because the first is a constant. Plus, once again, product rule, the first times derivative of the second. Now the second is a function to a power. So it's going to be the power times the function to the 1 less power times the derivative of the inside. First times derivative of the second, plus once again the second times derivative of the first would just be 0. So a prime would give us 2x over 4 pi, or the 2's cancel, dividing top and bottom by 2, we get x over 2 pi, let's see, minus 2 goes into 16 8 times, so minus 36 minus x over 8, and we're going to set that equal to 0. I set the derivative equal to 0. Once again, here we divided top and bottom by 2. Here we divided top and bottom by 2. 2 into 16 8 times, 2 into 4 twice. The minus here I threw over here to give us that minus sign. Okay, setting this equal to 0, we get x. We can transpose x over 2 pi is equal to 36 minus x over 8. Cross multiplying, 8x is 2 pi times 36 minus x. You can divide both sides by 2, or you can do that afterwards. If you leave it this way, 8x distributing 2 pi times 36 is 72 pi minus 2 pi x. Now I want to solve for x, so everything with x on one side, everything else on the other. 8x plus 2 pi x is equal to 72 pi. Since these terms all have x in them, I can factor out the x. I'm left with 8 plus 2 pi times x is 72 pi. X is equal to 72 pi over 8 plus 2 pi. And if you hadn't canceled the 2's up here, you can certainly cancel in here. But this is 2 times 36 pi. This is 2 times 4 plus pi. So we get that x is 36 pi over 4 plus pi inches. Now, we have to understand what that is and to see what that answers. Let's go back over here and make a little table. We're interested in maximizing and minimizing the area. We have to consider the interval. The interval, if you remember, ran from 0 to 36. I may have just erased that, but the interval was from 0 to 36. So, like that. The only value that falls in between is 36 pi over 4 plus pi. You work this out on your calculator, it's approximately equal to 15.8 inches. So it is a value in between 0 and 36. Now, what you have to do is figure out what the area is in each of these circumstances. Probably the easiest thing is to, if you have your TI-83 calculator, you could write the function in like this and use the table option to evaluate these various possibilities. Or you can use it directly. If x is 0, that's not hard, 36 squared over 16, and that turns out to be 81 square inches. On the other hand, if x is 36 pi over 4 plus pi, that's not exactly a picnic, and the calculator would certainly be helpful. Working that out on the calculator, I got 45.4 square inches for the area in that case, and letting x be 36, substituting in, that's the case where we don't make any square, it's all going to be circle, 36 squared over 4 pi, and that comes out to be 103.1 square inches. So these are our options. The largest of these is the absolute maximum. The smallest is the absolute minimum. So let's see what our conclusion is. We wanted to maximize and minimize the volume. The absolute max occurs when x is equal to 36 inches. X, if you'll remember, is the amount that you're using for the circle. So that means everything is being used for the circle. All the wire is used for the circle. And the absolute maximum volume in that case, of course, is 103.1 square inches. The absolute maximum volume, absolute maximum area, excuse me. The absolute maximum area is 103.1 square inches. The absolute minimum area occurs when x is equal to 36 pi over 4 plus pi inches. In other words, we take our wire, we cut here, and in this case, 36 pi over 4 plus pi inches is used for the circle. The rest is used for the square. So if this is about 15.8 inches for the circle, so 36 minus 15.8, or 20.2 inches, is used for the square. And in that case, the absolute minimum is 45.4 square inches. So 36 pi over 4 plus pi, about 15.8 inches, is used for the circle. The rest, 36 minus 15.8, or 20.2 inches, is used to form the square. In that case, the absolute minimum area would be 45.4 square inches. The last problem on this tape is the following. Maximize the area of a rectangle having one vertex on the parabola y equals 9 minus x squared, another at the origin, and the remaining two on the positive x and y axes respectively. Let's see what we can do here. We have the parabola y equals 9 minus x squared. If x is 0, y equals 9. If y is 0, x squared is 9, x is 3, or minus 3. Parabola looks something like this. And I'm interested in putting a rectangle in such a way that one vertex is going to be on the actual parabola. One vertex is going to be at the origin, and the other two on the positive x and positive y axes, so that it forms a rectangle. So for example, we might have a situation like this. This is a typical rectangle. We want to maximize the area of that rectangle. Now, understand, if the first point that I picked was like this, then the rectangle would look like this. If the first point was over here, then the rectangle would look like this. So there are certainly an assortment of rectangles that we could choose as we pick one point, one vertex on the curve y equals 9 minus x squared, and the other vertex at the origin, and then on the positive x and y axes. Okay. The point over here is the point x comma y, which is really x comma 9 minus x squared, since the y value is determined by the equation of the parabola. This is a point on the parabola, so its y coordinate is 9 minus the square of its x coordinate. The area of a rectangle is length times width. This dimension is y, but of course, it's 9 minus x squared. So, we want to maximize the area, which would be x times y, but we know that y is 9 minus x squared. And there is an interval. X is between 0 and 3. If x is 0, or if x is 3, you get a rectangle where one of the dimensions is 0. So you have a rectangle of area 0, or you could do it as an open interval. Okay, but we've had enough experience, we can do it as a closed interval. In either of these cases, you would have the area 0. And we're looking for the answer in between, which maximizes the area. A is 9x minus x cubed. We want to maximize this. We're going to take the derivative, which of course, with respect to x, is 9 minus 3x squared. We're going to set it equal to 0. 9 is equal to 3x squared, dividing by 3. 3 is equal to x squared. X is plus or minus the square root of 3, but on the interval x equals the square root of 3 is the only answer on the interval between 0 and 3. We're not interested in the negative square root of 3 here. And if we make ourselves a chart, x against the area, we have x equal to 0, x equal to 3, and the only critical number that we got was the square root of 3. The area in these two cases, if x is 0, going back in here, If x is 0, the area is 0 times 9, which is 0. If x is 3, it's 3 times 0, which is 0. And in the case where it's the square root of 3, it's the square root of 3 times 9 minus the square root of 3 squared. 9 minus 3, or 6. So we get 6, the square root of 3 square inches, or approximately 10.4 square inches for the area. So the ideal rectangle would, the maximum would occur this is 3, 0, this is 0, 0. We go over the square root of 3, which is about 1.7. And this would be the rectangle of maximum area. This is the point, the square root of 3 over, it is up, it's not exactly drawn to scale, it is 9 minus x squared, so this is the point, the square root of 3 over 6 up, this is the area, 6 times the square root of 3. That would be the maximum, the area of, the rectangle of maximum area that you could construct with these restrictions. And that brings us to the end of this tape.